Hi, my name is Andrew and I work as a mechanical engineer at a company that makes induction heating equipment. In this video, I'm going to show a method in which I try to determine the thermal conductivity of a piece of steel.
The constitutive law involving the thermal conductivity is Fourier's law, which is defined as Qs equals minus K dt dx, where Qs is the heat flux in watts per meter squared, K is the thermal conductivity in watts per meter Kelvin, dt dx is the temperature gradient in degrees C or Kelvin per meter. At steady state, there will be a linear distribution of temperature along the length of a solid with constant heat flux throughout the solid. The heat flux can then be written as minus K times T2 minus T1 over X2 minus X1. For my experiment, I'm going to try to control T1, and I will know X2 and X1, and I will try to control Qs in order to determine the value for K. So to do this, I have a bar of steel with length of 4 inches, 0.1 meter, cross section of 3/8 by 3/4 inch, and one end of the bar will be in a ice bath, which will be a constant temperature 0 degrees Celsius, and the other end I'll have a constant heat source, which I'll apply by using a power resistor with a known power input. And I'll measure the temperature at that surface where the heat source is applied using a thermocouple. Then you can rearrange that heat flux equation to solve for K, and this is what I'll solve for to estimate the value for thermal conductivity.
So this is my experimental setup. I have the steel bar immersed in an ice bath, and from the water line to the top of the bar is 4 inches, and at the top of the bar I have a thermocouple epoxied on and a power resistor. So the thermocouple is this measuring device, and that's data logging to my computer, and you can see right now it's cooling down since I put the steel bar in the ice bath, and once it reaches a steady state temperature where I can know the initial conditions, I'll turn on the power. Okay, so now after cooling down for about 20 minutes, it looks like I've reached about steady state conditions for setting this up, and I'm going to now turn on the power. By the way, at 5 degrees Celsius on the end of the bar where I'll be applying the heat. Now, to connect power, I'm going to turn this on. Okay, so now I've got 19.8 volts, about 20 volts on the resistor, and this is a 100 ohm resistor rated at 5 watts. About 20 volts is going to give me about 4 watts on this resistor. So now we can look back at the temperature plot, and we can see that the temperature is starting to increase already, and I'll let this go. Okay, so now I've reached steady state with the heat on, and actually the temperature is starting to climb a bit now because I stopped stirring the ice bath. So my final temperature was actually 37.4 degrees Celsius, and if I put that into my formula for calculating the thermal conductivity, I get K is equal to my heat flux, which I calculated, times the length divided by 37.4 C, my final temperature, gives me 59.7 watts per meter Kelvin, which actually agrees pretty well with published data for steel thermal conductivity. This published data is usually around 60 watts per meter Kelvin, so that's pretty cool. So another very useful equation we can look at with this scenario is the heat diffusion equation, which is a partial differential equation in x and t time. And now instead of t for temperature, I'm using u. So this states that the second partial derivative of u with respect to x is equal to 1 over alpha times the first partial derivative of u with respect to t, which is time. Alpha is the thermal diffusivity, which has units of meters squared per second, and is defined as K over rho Cp, with rho being density and Cp being specific heat capacity. Now, because this problem is a partial differential equation in x and t, to solve this numerically we need boundary conditions for the x components. So I have one boundary where I have a known constant heat flux from that power resistor, and at the other end we have the constant temperature of 0 degrees C being in the ice bath. So here we have written down the boundary conditions at x equals x1. The derivative of temperature with respect to x is equal to minus qs over k, and this is a Neumann boundary condition because it defines a rate at the boundary. And at the other end we have the temperature at x2 for all time is 0 degrees C, and this is a Dirichlet boundary condition because it defines a value of the function on the boundary. So we also need the initial conditions for temperature on the length of the bar at time t equals 0, and this equation takes care of that. At the beginning of this problem I let it reach steady state, but the whole bar wasn't at 0 C, it was actually a linear, assumed linear temperature gradient from one end of the bar to the other, where this temperature here was 5 degrees Celsius, had to look that up. And at the other end is 0 degrees Celsius. Then I also have alpha calculated here, where I'm using the value of K that I estimated from the first part, and rho and Cp are looked up from materials database. And it gives me a thermal diffusivity value of 1.75 times 10 to the minus fifth meters squared per second. Now I'm going to use these initial conditions and alpha and K in a MATLAB simulation to try to see how well my estimated values work in a numerical simulation. So here's the results of the MATLAB simulation. This solution was solved by using the MATLAB function PDEPE, and that's it right there. And to use this equation, it's a partial differential equation solver, and you have to generate your own definition function for the partial differential equation, an initial condition function, and a boundary condition function, and then it'll do the rest for you if you can figure out how to put those in the way it wants. And so this here is the 3D surface plot of the temperature over time. You can see the initial temperature here at this end, initial temperature distribution, and then the temperature at the end where I had the thermocouple measured. This is simulated solution, and at the end of the process you again have the linear temperature distribution from the hot end to the cold end. And I also have a plot of the experimental versus simulation data, and those actually agree pretty closely too, which is always nice to see. So thanks for watching.